So biconditionals take what we've been working on for the last couple days with our converse, our inverse, our contrapositive, and we're going to bring together two of these ideas. We're going to talk about having my original if-then, my conditional statement, and then the converse. Yesterday, when we were doing this, sometimes my if-then, my original statement, was true, but when we wrote the converse, when we switched around the hypothesis and the conclusion, it was no longer true. When I have a situation where the conditional and the converse are both true, we are able to do something more with it. And that something more is to write a biconditional statement. So as an example, if we have a student here named Aaron, he's planning to apply to admission to a culinary program. In order to get into culinary school, he has to earn a 3.5 GPA or higher, or he won't be accepted into the program. So I can take that idea right there, and I can write a conditional statement, an if-then, and the converse. So the original if-then would look something like this. If he earns a 3.5 GPA or higher, then he will be accepted into his culinary program. The converse, where we switch the hypothesis and the conclusion, would be if Aaron is accepted into the culinary school program, then he has earned a 3.5 GPA or higher for the semester. Both of those if-thens are true. If he gets in, it means he earned a 3.5. If he earns a 3.5, then he's going to get in. So both of these statements are true here. Because both of them are true, we can take these two statements, we can put them together into a single exclusive statement, meaning that these two things always have to go together. If one is true, the other has to be true. If the second thing is true, the first thing has to be true. They have to go together. So a biconditional statement is going to take the hypothesis and then it's going to use the words if and only if, and then it's going to have the conclusion. Hypothesis, if and only if, and then conclusion. So with this situation with Aaron, the biconditional statement would sound like this. Aaron will be accepted into culinary school if and only if he earns a 3.5 GPA or higher this semester. So in order to write a biconditional, I need an if, then that is true, together with the converse being true. If both of those are true, then we can write the biconditional which means writing an if and only if sentence. Let's practice doing this with a couple examples. So the first thing I need is an if-then statement. So let's look at Number 7, part A. It says, Rasha listens to music when she's in study hall. How can I take this sentence and write it as an if-then? If Rasha listens to music then she is in study hall. Beautiful. Is that true or false? So remember, when we're looking at an if-then statement, the first part's true, and if that means the second part has to be true, then the whole if-then is true. So if Rasha listens to music, then she has to be in study hall. Do you think that's true or false? Somebody that said false. Why false? You listen to music all the time. Where else could she be if she's listening to music? She could be at home, right? So this would be a false statement. She doesn't have to be in study hall if she's listening to music. That's what this sentence says. If she's listening to music, she has to be in study hall. She might be listening to music at home. So that, I would agree, that is a false statement. Now we need to take that original if-then, and we're going to write the converse. What was the word yesterday that I wrote down when we were talking about converse? Switch. We're going to switch the hypothesis and conclusion around. So instead of if Rasha listens to music, this will be if what? If Rasha is in study hall. Then what? Then she's listening to music. Based on the only information that we have about Rasha, which is this sentence that they gave us at the beginning, do you think this is true or false? If she's sitting in her study hall room, does that mean she's listening to music? Yes. So this part's true. Because the first statement is false, we cannot write a biconditional. They have to both be true if we're going to write a biconditional statement. Let's try this again. Let's practice this again. So part B says if two lines are parallel, then they have the same slope. They wrote our original if-then for us. So we are just going to recopy this sentence here on this top line. If two lines are parallel, then they have the same slope. What does parallel mean? Two straight lines. Where do they cross each other? Nowhere. Kind of like railroad tracks, right? Parallel lines never cross each other like railroad tracks. What is slope? What did you learn in Algebra 1 about slope? I see this. What is that? You don't know? What is slope? Slope is rise over run. There we go. Rise over run. So if I have two lines that never touch each other, they're parallel. Does that mean that they have the same slope? They have the same rise over run? Yes, it does. Yep. If they never touch each other, they're parallel, then that means that as I go from one point to the other on one of my lines, it would go, say, like up 5 and over 3. On the other line, starting from a different point to get to the next, I would go up 5 and over 3. I'm going to move in the same way to stay on that line, but because we start in different spots, they never touch each other. Help me write the converse of that now. Perfect. If two lines have the same slope, then they are parallel. Do you think that's true or false? If two lines have the exact same slope, they have the same rise over run, does that mean that they have to be parallel lines, that they're never going to touch each other? That is true. That is true. If they have the same slope, they have the same rise over run, then those will be two lines that never touch each other. So we have both my original if-then and the converse as true. That means that I can write a biconditional. So let's do that. We're going to write our biconditional statement. To write the biconditional, I need the hypothesis. Then I need the words if and only if. And then I need the conclusion. So let's look at our original if-then statement up at the top. If two lines are parallel, then they have the same slope. What is the hypothesis up here? Two lines are parallel. So that's how I'm going to start my biconditional. Two lines are parallel. And then we use the words if and only if. And now I need my conclusion. What's the conclusion? They have the same slope. Notice that this is a little bit different than my original if-then statement. I could have taken the converse and used this hypothesis with this conclusion to write my biconditional. It doesn't matter which one comes first, since up here the hypothesis is the conclusion down here, and vice versa. I need those two ideas with if and only if in the middle. Notice at the beginning of my sentence it doesn't say if. I've got if written twice here. I don't need it at the beginning also. And I don't have the word then when I write a biconditional. A biconditional has the words if and only if, but no then, no if at the beginning. Let's practice another one of these. Let's turn over to page 8. So we have the statement, isosceles triangles have at least 2 congruent sides. I need to take that sentence and turn it into an if-then. Isosceles triangles have at least 2 congruent sides. How can I turn that into an if-then? No, you're really close. I think what's happening, though, is like right at the beginning, you're taking 2 ideas because they have them side by side here, and you're keeping them side by side. And I think that's what's causing the confusion. So instead of saying if isosceles triangles, I'm going to say if it, or if a triangle is isosceles, then they have 2 congruent sides. Yes. If a triangle is isosceles, then they have at least 2 congruent sides, or then it has at least 2 congruent sides. And I'm going to cut down my writing a little bit by using the symbol for congruent instead of writing that whole long word out. If a triangle is isosceles, then it has at least 2 congruent sides. Is that true or false? If a triangle is an isosceles triangle, yes, that is true. Isosceles triangle means at least 2 of the sides are congruent. Mm-hmm. How would we take that now and write the converse? Perfect. That's exactly right. If a triangle has at least 2 congruent sides, then it is isosceles. Perfect. Is that true or false? Yep, that is true. I liked your answer of yes. I got the idea. Those are both true. Since they're both true, what does that mean I can do now? We can write a biconditional. All right, so we want to write this biconditional. We start with the hypothesis, and it doesn't matter whether I look at the original if-then or whether I look at the converse. But I need the beginning part. How should I start my biconditional? A triangle is isosceles. And after I write my hypothesis, what do I need? If and only if. A triangle is isosceles if and only if what? It has at least two congruent sides. You guys are knocking this out of the park. Fantastic job. Let's see if we can take and switch this up just a little bit. I'm going to give you a biconditional statement. And I want to take that biconditional statement and pull it apart to write an if-then and then to write the converse. And then we're going to decide whether those things are true or false. All right, so I want to look at number 8. The biconditional that I'm giving you is two angles are complements if and only if their measures have a sum of 90 degrees. So let's start by writing our original if-then. How does my if-then have to start? What word has to go at the beginning? If. So if what? If two angles are complements, then what? Then their measures have a sum of 90 degrees. Is that true or is that false? That's true, yes. If two angles are complements, then their measures have a sum of 90. So if two angles are complements, then if I take their measurements and add them up, I get 90 degrees. All right, let's write the converse. What does the converse look like? If two angles measures have a sum of 90 degrees, then they are complements. If two angles measures have a sum of 90 degrees, then they are complements. Is that true or false? That is true. So my conditional is true, and the converse is true. So is the biconditional true or false? True. They both have to be true for the biconditional to be true. All right, let's try one more like that. I'm going to start with the biconditional of x is greater than -2 if and only if x is positive. Let's write an if-then from that. What would this look like? Yep, if x is greater than -2, then x is positive. If x is greater than -2, then x has to be positive. Is that true or false?
False. Because
Why? What else could x be? It could be -1. So this is false. X could be -1. Is that the only possible thing that x could be to show that this is false? It could be 0. Or could it be -0.5?
Yes.
Could it be -1.5?
Yes.
Could it be -1.99? Yeah, all of those work. All we needed was one example to show that it's false. So we just had to give one number here. So x could be -1, or x could be 0, or x could be any of those things that are in between -2 and 0 on the number line, because we want x to not be positive but still be bigger than -2. All right, let's write our converse. So let's swish it around the other way. What would this look like? Yes, if x is positive, then x is greater than -2. If x is a positive number, does that mean it has to be bigger than -2? Yep, that one is true. If I have a positive number, it will be further to the right on the number line than -2 is. Okay, so our original if-then conditional was false, but the converse was true. So what does that mean about the biconditional? It's false. They both have to be true for the biconditional to be true.
Oh, so first of all, with the converse, so pretty much what it's saying is that every positive number, if like, so if x meant every positive number, then x being greater than -2 would be true.
Yep.
Okay.
If x is any positive number, then whatever it happens to be would have to be bigger than -2. Okay. That's what that converse is saying, yes.
And also, so for the biconditions to be true, both the conditional and the converse have to be true?
That's absolutely correct.
All right.
Both the conditional and the converse have to be true in order for the biconditional to be true. If one of them is false, or if both of them are false, the whole thing is false. Very nice work. So the homework that's due for tomorrow, we have now finished all the stuff that you need to do that. We've talked about conditionals, writing if-thens. We've talked about how to identify the hypothesis and the conclusion, how to write the converse, the inverse, and the contrapositive. And now we've talked about biconditionals. That's what's on the homework that's due for tomorrow. We're going to spend the rest of our class period pushing forward into the new stuff that we're going to be doing. This will show up on the next homework assignment, but we're going to start working on it right now. So let's go over to page 9. And you guys are going to need the red paper that you got on the first day of this module. So go ahead and pull that red paper out. We're going to be using that now. Pull the red paper out. We're on page 9 now. We're going to begin talking about something called proofs. This is how I show that an if-then is always true. If I think this is a true statement, then I have to be able to go through and prove it. So I want to practice writing a proof with something that feels a little bit more familiar. Over here in this box on the left, somebody has worked out an algebra problem. And what we are going to do over here on the right is give reasons for why we are allowed to take those different steps. So if you look at your red paper, down the left-hand side of the sheet has reasons that we are allowed to use in proofs. This is on the front and the back. There's reasons down the left-hand side. And on the right-hand side, it has some examples of what that looks like in a problem, what that looks like in steps. My first reason in a proof will always be because that's what was given to me. That's where I was told to start. So my first reason is always, well, this is what I was given. So I want you to look at this first line, this top line. That's the original problem that they were given to solve. And then I want you to look at the next line down. Some things changed. What happened between that first line and the second line? They distributed. They took this negative 10 and they multiplied inside the parentheses with that. And I love that you use that word distributed because that's one of the properties from our red page. We just used the distributive property. All right, so now I want to look here on this second line, and I want to compare that to the third line. What changed between the second line and the third line? What'd you say? Yeah, they took this and they added 30x to both sides. So they made it cancel out over here. That's why we have just the 60 over here now. And then they combined the 4x and the 30x to get 34x. If you do it to one side, have to do it to the other side. Whenever we do things to both sides like this, because that's the rule, that's called a property of equality. What operation got done to both sides? Addition. So this is the addition property of equality. And I cheat a little bit on writing this all out. All right, let's look at what happened now. So now I'm looking here. They subtracted 2 from both sides. So what do you think we would call that property? Subtraction property of equality is absolutely right. All right. Then what did they do? Then they divided. So what would we call this? Division property of equality. And then this last step is a little bit weird because that looks like almost exactly what was up above, except which side of the equal sign is x on down at the bottom? It's on the left, right? Which side of the equal sign is x on in the step right above it? It's over here on the right. So x switched sides of the equal sign. When we have an equation, x equals 5, and we switch it around the other way, 5 equals x, we call that the symmetric property. things that are symmetric are the same on both sides. So the symmetric property allows me to flip it around the other way because it's the same on both sides. Fantastic so far. So I want to spend the rest of our time. You guys have just done your very first proof. Congratulations. We're going to begin doing geometric proofs starting either tomorrow or Monday. It depends on exactly when we get to it. So I want to practice looking at this red paper and looking at some examples and seeing what reason we would use. So I'm down here on number 2 inside these boxes, and I'm starting with part A. The if is what I'm starting from. So that's my given. And then I want to know what property it is that would allow me to move from my if to my then. So I'm looking for what's different or what changed. So if this is where I start, QR equals ST, what's different about my then? It has BC. Does it have it on both sides? What operation got the BC there? Addition. It says plus BC, and then over here it also says plus BC. So they added something and they did it to both sides. What did I say we call that? Addition, property of equality. When you add the same thing to both sides, that is the addition property of equality. All right, now I'm looking in the middle at part B. It says in my if, the measure of angle ABC is equal to the measure of angle KMR. What changed between my if and my then? They switched it around. What did I say that was called? Symmetric property.
Why is it just property, not property of equality?
It's not a property of equality because we didn't do the same thing to both sides. We just flipped the sides. When you do the same operation to both sides, then it's a property of equality. Part C is a little weird. I don't even have an if and a then. I just have that AX equals AX. Yep, reflexive property. The reflexive property is when I say that something is equal to itself. So x equals x, or 5 equals 5, or in this case, ax equals ax. When I have something equal to itself, that is the reflexive property. All right. Let's look at part D. This if has 2 pieces to it. It says the measure of angle 1 is equal to the measure of angle 2, and the measure of angle 2 is equal to the measure of angle 3. So both of those things are part of my if. What happened down here in my then? Yeah, they took the measure of angle 1 from up here, and they said that it's equal to the measure of angle 3 down here. What property is being used here? Look on your red paper. Transitive property. The transitive property happens when I've got 3 things. It's always when I have 3. And I say the first one is the same as the middle one. And the middle one is the same as the last one. If that's true, the first is the same as the middle is the same as the last, then the first and the last are also the same as each other. So, for example, if I have the same amount of money in my pocket as you do, and you have the same amount of money in your pocket as your sister does, then I have the same amount of money as your sister, because all three of us have the same amount. That's the transitive property. All right, E. Here's my if. Here's my then. What changed? The 2. It moved. How did it move? It went from multiplication to division. So they did what to both sides? Did they multiply to both sides to move from one to the other, or did they divide? They divided on both sides. So this would be the division property of equality. Part F, JK plus AB equals RQ plus AB. And then we get down here, and what happened? AB got eliminated. What operation lets me take things away? Subtraction. Did they do it to both sides? Subtraction property of equality. Two more to go and then we're done. If AB plus BC equals AC and BC equals DE, then AB plus DE equals AC. What's different down here from my then? The order. What changed? I heard BC. Where is BC in my then? It's DE. So we took one thing out and we put something else in. What lets me take something out and put something of equal value in? Substitution. All right, last one. Nope, that'll wait until tomorrow. Homework is due tomorrow. We'll finish up this and page 10. You also have your first skills check tomorrow. First skills check tomorrow. Homework number 2, which is the very bottom paper over there.